pleasure to welcome you to the 20th Hofstadter lecture. Looking around, I noticed that most of you were present in yesterday's talk, so I will not make a long introduction and take time away from our speaker. This is the second talk to honor Bob Hofstadter. As Fabiola said yesterday in the public talk, the very successful LHC detectors and the extremely successful LHC experiment are a testament to Bob's influence and contributions to science. I want to again thank Laura and Doug Hofstadter and friends for their generosity, for the support of this lecture series that allows us to bring outstanding physicists in our community. Today it's a pleasure to welcome our multi-talented and multi-awarded speaker, Fabiola Gianotti. She has had a stellar career. She was the head of the Atlas collaboration, the crucial years from 2009 until about a month ago. And on our Independence Day, she was assigned the task of reporting to the world the discovery of the Higgs particle. She has won several awards that I enumerated yesterday. I'll just point out the Fundamental Physics Prize of the Milner Foundation, as well as the unique for a physicist, one of the finalists of the Times Magazine Person of the Year Award. And without further ado,
thank you. Thank you, Savas. You won't believe it, because when you are a spokesperson of an experiment, you are supposed to be very, very open. I'm quite a shy person, so I must say. Thank you to Savas and the committee of the Bob Hofstadter Memorial Lecture for selecting me and for these lectures and for giving me this pleasure and honor. So many of you were already following the public lecture yesterday. Today I will be a little bit more technical, and will try to avoid too much overlap with what I've shown yesterday. So clearly we know that Bob Hofstadter has been one of the pioneers of accelerator-based particle physics at the energy frontier, and we know, of course, that the LHC is the accelerator at the energy frontier today. So I thought that I would show you these spectacular events, because it illustrates very well what is the energy frontier today. This event was recorded by Atlas in August 2012. It's an event where two jets have been produced from the two high-energy quarks or gluons have been produced in the elementary collision of the constituents of the two colliding protons, and these quark or gluons have fragmented into jets of particles. Look at the energy of these two jets, 2.2 to 2.3 TeV. So each one of these jets has the same energy as the Tevatron collider at Fermilab, essentially. And if these two jets were produced by a particle, one particle, this particle will have a mass close to 5 TeV. So this is really the energy frontier. We are exploring this multi-TeV region. For perhaps the experimentalist among you who perhaps can appreciate the precise measurement of these jets, by the way, that this SLAC Atlas team has contributed a lot to the measurement of jets and to optimizing the techniques to measure jets well. The missing energy of the event, so this event, which is a 5 TeV event, is only 50 GeV, meaning that the jets are extremely well measured by the calorimeter, because if they were not well measured, that you will measure some missing energy coming from fluctuation and from resolution effects. So this is really a gorgeous event. Okay, so Sava mentioned the 4th of July, which is still in our eyes and our hearts. It was a historical day when Atlas and CMS announced the discovery of a particle, which at the time looked very much as the Higgs boson, but since then we have made some progress, and I will show to you today some precise some measurements of the properties of this, our new friend, as I like to call it. And that day was the culmination, or at least the first culmination of a very long path. And let me go through a bit the history, because I think it's important to remember that the discovery of the Higgs boson did not come like that just by chance. First studies for a high-energy proton-proton collider in the LEP tunnel, in the existing 27-kilometer underground ring, which was built to house the E+ E- machine LEP, which has been running between 1989 and 2000. First studies happened in the mid of the 80s. And actually, I think we have to thank those people, those visionary people, who in the beginning of the 70s, when they decided to build the +E- LEP collider, were visionary enough to build a tunnel large enough to be able to house in the future a hadron collider, which will require more space. And thanks to the visionary view of those people today, I mean, we could build the LHC in the same tunnel without excavating another tunnel. So in '84, first discussion, first studies for the physics case of this hadron collider in the LEP tunnel. The LHC was actually approved by the CERN Council 10 years later, and the year before, 1993, the SSC was cancelled, and US physicists joined the LHC. So this was very good for the project, because they've made very important contributions to the project. 2 years later, construction of the machine, of the collider, and the experiment started. Installation of the accelerator and experiment in the underground tunnel and cavern started in 2003. And in 2009, on the 23rd of November, first beams were circulated in the LHC, and they collided at injection energy, so 450 GeV per beam. And then 3 months later, on 30th of March, first collision at 7 TeV in the center of mass, 3.5 TeV per beam, inaugurated the exploration of a new energy frontier, and hopefully a 20-year-long program. So you see, in total, if you are going to operate the LHC for another 20 years, in total a 40-year project from first ideas to operation and then full exploitation. 2 years later, the energy was ramped up to 4 TeV per beam, so 8 TeV, and this was really an important step to be able to discover the Higgs boson fast. And on 4th of July, as already mentioned, the announcement of the discovery. And on the 14th of February of this year, we ended the first LHC run 1, as we call it now, finished. And we started a 2-year-long shutdown called LS1, and I will come back to this later. So I would like to stress that the LHC has required the development of most innovative technologies in many fields: superconducting magnets, cryogenics, electronics, data transfer and storage, instrumentation, etc. It has required the development of a new concept, but also a lot of ingenuity, patience and idea to address unforeseen events. We had a lot of challenges to solve during the long path of construction of the machine and experiment. We had to face a lot of problems, of course, because we were building high-tech instruments. There were accidents on our paths. Everybody remembers, well, we remember very well the accident on 19 September 2008 at 11:30 a.m. when the, yes, unfortunately the LHC exploded in some sense. A little interconnects between superconducting magnets, where the soldering was not done in the quality control was not optimal, actually broke, releasing helium in the tunnel, which broke and displaced several magnets, and and this stopped us for 1 year. This was really a very bad moment, but then I think we recovered well. And huge efforts of the worldwide community in terms of ideas, technology, money, and people. So this is what we have today, the LHC tunnel, 27-kilometer ring. This is the injection chain, the SPS, the previous accelerator, and 4 experiments. As you know, Atlas and CMS, these are called general purpose experiments. So experiment able to explore the new energy frontier and to detect anything, everything that nature has decided to put there, hopefully something. Well, at least the Higgs boson was there. And then two molar experiments, LHCb and ALICE, devoted to some specific studies. So LHCb is studies B mesons, and so try to understand the origin of matter-antimatter asymmetry in the universe. And ALICE is devoted to the study of heavy ion collision, because the LHC is also able to accelerate and collide heavy ion beams. SLAC is involved in ATLAS. There is a very strong team working on our experiment. So here I will concentrate on the ATLAS experiment. Of course, CMS has a very similar potential and very similar results, but as a test case, I will mainly concentrate on ATLAS. And just before start, let me remind you what the ATLAS SLAC team is doing. They have a total about 50 scientists, including physicists, engineers, and also very many students and a postdoc. And they've made very strong contribution to all components of the experiment, from detector construction to detector operation, to now upgrade to address the next phase of the LHC, software and computing and physics analysis. And so here are some examples of what they've been doing or are still doing, like, for instance, development of 3D pixel sensor, high-tech pixel sensor, readout electronics or in particular also for the upgrade, trigger and net acquisition, simulation, detector performance studies. I mentioned the precise reconstruction of jets, and physics, supersymmetry in particular, the very important third generation. I will come back to this later, Higgs physics, and they have also a very strong computing center. So this is ATLAS. It is essentially as the shape and the structure of a typical collider detector. Is made of several concentric cylindrical layer in the central part, closed in the forward region by two end caps. And of course, the goal is to surround almost completely the collision region, and to detect as many particles as possible. So close to the beam line, it has an inner detector made of silicon pixel, 100 million of 80 million of silicon pixel of size 40 micron. Is actually one of the most, perhaps the most high-tech component of the detector, followed by silicon strip, a transition radiation detector. This is a gas detector which allows tracking and also particle identification. So this inner detector is immersed in a magnetic field and is used to reconstruct charged particles, measure their trajectory and their momentum. It is followed by an electromagnetic calorimeter used to measure electrons and photons, measure their energy, direction, identify electrons and photons. And this detector is a sandwich detector made of lead absorber plates and liquid argon as the sensitive medium. This is followed by a hadron calorimeter made of iron and scintillating tiles in the central region, and in the forward region liquid argon again, and liquid argon because liquid argon is extremely resistant to radiation, and the radiation levels are the highest in the forward region. And finally, the external muon spectrometer is made of muon chambers, these blue objects, in air, immersed in very strong magnetic field, which are produced by a very powerful and say very big and very high-tech superconducting toroidal system. Also important is the online selection of the events. The beam collides, the two proton beams are not made of, the proton beams are not a continuous flow of particles, of protons. The protons are grouped in bunches, and this bunch are separated by 50 nanoseconds. Every bunch contains something like the maximum we reached was 1.5 10 to the 11 proton per bunch. Now we are running with a bunch separation of 50 nanoseconds. In 2015, the bunch separation will be reduced to 25 nanoseconds. So these beams, until now, have been interacting 20 million times per second. This was the interaction rate. And so, of course, we cannot collect all the events that have been produced in this collision, and not all of them are interesting. Actually, most of them are not particularly interesting, are very well known soft proton interaction or hard scattering interaction, which are not particularly interesting. So, and we cannot, of course, record all of them. So we have to select very quickly online only a fraction of them. So out of this 40 megahertz collision, or 20 actually until now, we can only record a few 100 hertz, 200 to 400 hertz. And so this means that online we have to decide which events we record and which events we discard, and the events that are discarded are lost forever. There is no way to recover them, and of course you don't want to throw away Higgs events, so you have to be very careful in what you do, and SLAC has been working on this as well. So note the size of this detector, very 45 meter long, 25 meter high. These are human beings, to be equal opportunity. We have a man and a woman, so let's see. And but at the same time, as I also mentioned yesterday, we have to track with very high precision 1,000 of particles that are produced in the collision with a precision of 10th micron typically. That's why we have very granular silicon pixel detector very close to the beam line, where the track density is the largest. And also, of course, it's very important for this detector to have a fast response between 25 and 50 nanoseconds because of the very high interaction rate of the two beams. Now, construction is not enough. The very stringent performance requirements dictated by physics have required a huge amount of painstaking work, quality control, test with beams, without beams. Every single piece of detector has been, for instance, tested for radiation hardness, for stability, etc. And also very high stringent requirements on the precision with which these instruments have been built. The mechanical precision, the precision of the electronic chain, etc. And I would like to give you one example, which is not only very close to my heart, but of course very important for the Higgs to gamma gamma discovery. Very close to my heart because as a young student, I've worked in Milano on the liquid argon electromagnetic. Yeah, this is me when I was young, much younger. I work on the construction of the first prototype, actually, of the liquid argon electromagnetic calorimeter, fundamental instrument to observe the Higgs into the gamma gamma final state. This detector, liquid argon calorimeter, are quite classical, traditional instruments in energy physics. They've been pioneered in the early 70s by Bill Willis and collaborators. But the problem is that typically liquid argon calorimeters are very slow detector. So although they have very good feature for the LHC because they are extremely resistant to radiation, so they were very good given that this machine is a high radiation machine, unfortunately they were too slow in terms of response, few microseconds, to be able to run at the 25, 50 nanoseconds we need at the LHC. And so at that time we had, not me, but a group of people developing this technology. I participated, but I was very young. The idea of bending the plates and the electrons and absorber plates into an accordion shape. And this was the trick which allowed us to build a fast liquid argon calorimeter to operate at the LHC. So the first prototype that we built was appeared in the early 90s. Then this picture showed the installation of the calorimeter in the underground cavern in October 2004. This is the cylinder is a cryostat containing the detector. Argon becomes liquid at 87 Kelvin, so you need cryogenics, okay? And then this is the first pi0 to gamma gamma peak that we observed in December 2009, just a few days after first collision at 900 GeV at injection energy. So you see it's a very nice peak, and I will show you soon, of course, our X to gamma gamma peak. Now, why I'm showing that? Because construction is not enough, and to observe a X to gamma gamma peak on top of the background, you need an excellent mass resolution, so an excellent resolution of the calorimeter, and you have to be very careful to the details. These are experimental details which show you that getting the Higgs is not so easy if you really don't do this kind of foundation work. So actually, 1% variation in the absorber, in the thickness of the absorber plates of the calorimeter can produce a 0.5% response drop in the calorimeter response, okay? And so if you have these non-uniformities in the absorber plates, then of course when you reconstruct your Higgs to gamma peak over the full calorimeter coverage, then this peak becomes extremely broad if your calorimeter is not built with very high precision. So this implies that in order to observe such a peak and not to deteriorate the Higgs to gamma mass resolution, the thickness of the absorber plates of this calorimeter had to be controlled at the level of 10 micron. These are very big absorber plates, few square meters, and to control their thickness at 10 micron is not easy. So this plot shows the distribution of the thickness of the 2048 absorber plates of the barrel calorimeter, this object. You see the average value is 2.1 millimeter. It was measured with the X-ray machines and ultrasound machines, and the RMS is 10 micron. So actually, we met this with this very stringent requirement. But this is only one of the examples of the very detailed work that we had to do to observe a narrow peak on top of the background fast, quickly, because of course, if it takes many years, of course, you can do it. But okay, so since first collisions in 2009 or better 2010 at high energy, the accelerator experiments and the computing have been working extremely well. So we have recorded a huge amount of data. Atlas has recorded 5 billion events. We have 5 billion events to tape or to disk. So we have remeasured, of course, rediscovered the standard model and the known particles. I will show you some example of the known processes that we have measured at 7 and then 8 TeV. We have explored many physics scenarios beyond the standard model. So as I mentioned yesterday, these are scenarios which try to overcome the weaknesses of the standard model and to address the question the standard model is not able to answer. And then, of course, we have discovered the Higgs boson. Now, one of the key elements for the fast discovery of the Higgs boson has been the superb performance of the accelerator of the LHC machine, which is an extremely complex superconducting machine, 27 kilometers of high-tech magnets, and has been working very well. In particular, it has achieved a peak luminosity of 7.7 times 10 to the 3 centimeter to the minus 2 second to the minus 1. To give you an idea, this is 20 times larger than the luminosity achieved at the Tevatron Collider at Fermilab. I remind you that the luminosity is a parameter which is proportional to the intensity of the two beams, because it goes as a square of the number of particles circulating in the machine, and is inversely proportional to the beam transverse size. So you want to squeeze your beams very much and have them very and put in the beams as many particles, as many protons as possible. So why it's important to run at a very high luminosity, very high beam intensity? Because the number of events that you can observe due to a given process is given by the cross-section for producing that process in proton-proton collision times the integrated luminosity. So the peak luminosity integrated over time, which is a parameter proportional to the amount of data that you collect. So if you want to observe very rare processes, then you need to produce a lot of collision, of course, and have very intense beams. And so this explains why we are running in with such high luminosity. So this plot shows the integrated luminosity as a function of time delivered to Atlas by the LHC in 2010. You see very little, it was a lot, but it was of course a little compared to what we got later on. In 2011 at 7 TeV and in 2012 at 8 TeV. On the 4th of July, we had something like about 5 inverse femtobarn of integrated luminosity in 2012, plus another 5 in 2011, plus another 5 in 2012. And today, we have something like a factor of 4 more in integrated luminosity than we had in July. So in total, about almost 30 inverse femtobarn, 3 more, say. I would like to say something else here, but yeah, okay. So the price to pay for this very high luminosity. So yeah, this is the thing I want to say. 30 inverse femtobarn that Atlas has more or less, well, a bit less, 25, 27 inverse femtobarn. 30 inverse femtobarn is 3 times more than CDF and D0, the Tevatron experiment. So CDF and D0 in 28 years of operation have recorded each 10 inverse femtobarn. Atlas and CMS in 3 years of running at the LHC have recorded 30 inverse femtobarn. So this gives you an idea of the power of this machine. Now, the price to pay for the high luminosity that the experiment had to face, and which was to some level unexpected to be so striking and so fast, is what we call pileup. Pileup is simply the number of simultaneous proton-proton interaction per bunch crossing. So you've seen that I said the protons are grouped in bunches separated by 50 nanoseconds. Every bunch contains 1.5 times to the 11 protons. When you collide these two bunches, they are so intense that the probability to have more than one collision is large. So in one collision of the two bunches, you can produce a Z, you can produce a Higgs boson, but at the same time, simultaneously, you produce many other interactions. So when we were running in 2010 with relatively low intensity of the two beams, typically a couple of events, 1, 2 events, were produced per bunch crossing. So if you look at what happens in your detector, this is a transfer view of Atlas. The beams are going, one beam is going into the screen, the other one coming out, orthogonal. You see several particles produced in the collision, but after all, the event is quite clean. You can track them almost by eye. In 2011, the beam intensity went up, and this is the typical number of tracks produced in a collision. In 2012, the luminosity intensity went up even more, and so this is a typical event that we had to deal with in 2012. To give you a better image, that's it. So this is an event, okay, in which at a given bunch crossing, a Z boson decaying into 2 muons has been produced. Here you can see the 2 muon tracks coming out of this vertex, but in the same bunch crossing, an additional 24 proton-proton interaction, soft interaction have happened, and so you see that the event is particularly crowded. So this is not an exception. This was the normal condition in which we have been working in 2012. At the beginning of the fill, when the beams were injected, typically we were working with 40 simultaneous collisions in the detectors, then going down to much less at the end of the fill after 8 hours or so, but on the average we had something like 25 reconstructed vertices. So this was really a big challenge from the experimental point of view to try to extract, in this case, a Z, 2 mu, but it can be Higgs, from this very large number of interaction in the same bunch crossing. So I mentioned that we recorded a huge amount of data, and so we of course have had already a huge scientific output. So you can see, as a function of time, the number of papers submitted to Atlas. Some of them have been already published, others are still with the journal. But in total, as of today, we have submitted 240 papers. And in 2012, we have published 123 papers. And this is the single most productive collaboration in 1 year ever. Nobody has ever published 120. So the second one is the competitive experiment, CMS, with only 90 papers. Okay. Okay, so now we hope to publish even more, of course, because we have a fantastic data sample. So if we take all our data, 25 to 30 inverse femtobarn, depending on our data quality, etc., we have today, after all selection cuts in our data sample, we have 100 million W boson decaying to lepton neutrino, 10 million Z boson going to lepton pair. This is as much at the LEP collider in 10 years of operation. This is what we get. 500,000 top quark events going to lepton plus something else. 600 Higgs candidates. So the LHC is becoming a Higgs factory, not yet there, but almost. By the way, when you run at the maximum peak luminosity, 7 times 10 to the 33 centimeter to the minus 2 seconds to the minus 1, we produce one, well, the LHC produces 1 Higgs to gamma gamma every 50 minutes, and 1 Higgs to 4 leptons every 14 hours. So we are approaching the level of Higgs factor. Okay, so we'll only give you some examples of achievement and what we have done so far. So we have measured the cross-section for known processes, standard model processes, W production, Z production, PT bar, single top, die boson, so pairs of W or WZ, single top, etc. So you can see here the various measurements at 70V in red and at 80V in blue. These measurements are important on their own, of course, because they test the standard model in this new energy regime, and you can see that the experimental point here are in good agreement with the theoretical prediction given by these horizontal bands. So the standard model works well at 7, 8 TV, which is on one side good news. They're also useful because these processes are backgrounds to searches for new physics. Note that in some cases the experimental precision really start to challenge the theory, like for instance in TT bar top pair production, you see the theoretical error and experimental error are very comparable, so this of course requires some additional work from our friend theorists. We have also looked for physics exploring a huge number of new scenarios. Supersymmetry is not included here because I will come back to this later, but extra dimension, composite, new gauge boson, contact interaction, everything. You can see many of them. We have found nothing until now, and so we have put limits on particles predicted by these scenarios between typically 1 TeV and 10 TeV. You see, we extend typically well beyond the 1 TeV. Does the microphone work? Yes. Okay, fine, thank you. So several TeV in many cases. So question, should we be desperate? Well, I will say no. First of all, because the searches we have been doing until now with the present data set are far from being complete. We have, of course, excluded the easiest scenarios, but of course, new physics may still hide in the present data in some corners. And second, because the center of mass energy today is only 1.7 times smaller than the design value, which will be reached in 2015, and the integrated luminosity, so the amount of data is a factor of 12 smaller than the design value. So there is, of course, hope to be able to find new physics soon. So let's now move to Higgs, and I will not talk about Higgs searches, but Higgs studies, because we have moved now from the discovery phase to the measurement phase. So I will show you a couple of examples of the signal in the two very important channels, gamma and 4 leptons, and then show you what kind of measurement we have made so far of this new particle. The results I will show here are the most recent results based for the most sensitive channel, gamma, 4 leptons, and lepton neutrinos on the full data set that Atlas has recorded so far. So I remind you briefly that the Higgs boson is produced at Hadron Colliders, in particular the LHC, through these main 4 diagrams. The fusion of 2 gluons coming from the 2 protons through a loop involving top quarks. It can be also produced in what we call vector boson fusion. So the coming quarks radiate a W pair or a Z pair, which produce, well, actually W pairs, which produce a Higgs boson. And then these 2 incoming quarks go out in the final states in the forward direction of the detector, so giving rise to a very specific signature. The Higgs boson can also be produced in association with a W and a Z, mainly a W, and also in association with a top anti-top pair. The cross-section at 125 GeV is huge, the order of 20 picobarn, which is 20 times larger than at the tevatron. However, unfortunately, at Hadron Collider, most of this cross-section cannot be used because most of it is, in most cases, the Higgs decays hadronically in B anti-B quark pairs, and inclusive production of Higgs going to BB bar cannot be extracted from a huge background at the Hadron Collider. So we have to rely on final states containing leptons and photons, thereby rejecting actually most of the cross-section. So in the region where the Higgs is sitting, 125 GeV or so, the most sensitive channels are, in decreasing order of sensitivity, the most important are X to gamma, X to 4 leptons through a pair of Z, and X to 2 leptons, 2 neutrinos through a W pairs, followed by X to tau tau, and X to BB bar, where the Higgs is produced in association with the W and the Z, which produces leptons in the final state, and so allows us to extract these final states from the background. These channels are very challenging for various reasons. In some cases, like X to 4 lepton, the signal is very tiny, a handful of events. It's a rare process. In other cases, like X to gamma gamma, there are a lot of events produced, but the signal to background ratio is very small, few percent. In other cases, like WW, the final, or tau tau, BB bar, the final state are extremely complex, and there are many backgrounds contributing. So I would like, first of all, before going to a couple of examples, also to acknowledge, because of course I talk a lot about building instruments, building machine, accelerator, experiments, but also there's been a huge effort over the years by the theory community, also from SLAC and Stanford, to compute higher order correction to this cross-section for the signal, but also for the very complex, often very complex backgrounds, which has allowed us to, when comparing the simulation to the data, to really find good agreement right from the beginning, and this has also, again, been very crucial to be able to discover this particle quite quickly. Okay, so I will now show you a couple of examples, the two most sensitive channels, X to gamma gamma. So X to gamma gamma is a very simple topology. The Higgs decays into 2 photons, so you have 2 high energy to high PT photons in the final state, quite simple. However, the analysis is quite complex, because in order to increase sensitivity to the specific production processes, like for instance vector boson fusion, like this one, which gives you access to the different couplings of the Higgs, the events are divided into various categories: events with 2 photons and no additional jets, events with 2 photons and additional jets in the forward region, events with 2 photons and leptons, so it's quite complicated. Now, this final state has the problem that the signal to background ratio is very small, at the level of 3%. Inclusively, it goes up in these categories with additional jets, because of course they are more pure. So the single most important experimental issue to extract a signal quickly, as we did, is to have an excellent mass resolution of the calorimeter in order to see a narrow peak due to this resonance on top of the background. So I already mentioned the properties of the calorimeter, so I don't think that I will spend additional time and just show you the present situation. This is the X to gamma gamma spectrum, the gamma gamma spectrum that we have now. So here you can see the invariant mass, the spectrum, the mass spectrum for events with 2 photons in the final states, containing the full data samples recorded until now, and you can see a smoothly decaying spectrum due to well-known processes giving rise to 2 photons in the final states. And you can see already just by high a peak here, 125 GeV, which is even more evident when you subtract the background. So I think this signal now is so visible that you don't need to apply any statistical technique. But if you want to quantify exactly the significance of this peak, you plot what is called the so-called p-value, which gives you the probability that what you observe here is due to a fluctuation up of the background. It's not a signal, it's a fluctuation. What is the probability? So you look at this p-value distribution, you see that the probability around 125 GeV is very small, is 10 to the minus 13, which corresponds to a significance of this signal of 7.4 sigma. I remind you that the standard for claiming a discovery is 5 sigma. On the 4th of July, we reached 5 sigma combining together all channels. And now we have 7.4 sigma with X to gamma gamma alone. So we have discovery in the individual channels. Actually, from a standard model Higgs going to gamma gamma, we would expect a smaller signal, 4 sigma. So the signal that you observe seems to be a bit higher, 1.6 times higher than expected from the standard model. So we'll come back later on this. This is a gorgeous event recorded by Atlas. You can see here the collision, okay? 2 photons produced in the calorimeter, extremely clean, and 2 jets in the very forward region. So this is a candidate for vector boson fusion, where this particular process where these two jets are produced in the very forward region of the detector. Okay, next channel, and then I will go to the summary for the Higgs. X24 lepton through 2Z. This is a completely different final state. The cross section is very small. This is a very rare process. It's a 20 times smaller than the Higgs to gamma gamma. However, this channel is extremely poor. The signal to background ratio, which is 3% in gamma gamma, you have seen how big is the background in gamma gamma. In this case, is almost 1-to-1. Okay, so just a few events, a handful of events clustering around a given mass will be very, very convincing. So you typically, so we select events containing 4 leptons, electrons or muons, and because these 4 leptons are relatively soft, because the Higgs has a mass of 125 GeV, you divide this mass by 4 typically, and so you get a few GeV electrons. It's very important to have very good reconstruction, lepton reconstruction and identification efficiency down to very low PT. So we spent a lot of time at the end of 2011 to optimize the sensitivity of our analysis to cover as much as possible the leptons down to very low PT, and so to capture as much as possible of this signal, because as I told you, it's a handful of events, so every single event you can get. This is, of course, a big improvement, and we spent a lot of time to make the lepton reconstruction efficient and robust against pileup. So this plot, for instance, is very nice because it illustrates the result of this work, which was fundamental for the discovery. It shows that the electron reconstruction efficiency as a function of the electron PT as obtained in 2011 with the 2011 data and in 2012. You can see the improvement in 2012 thanks to this very hard work, foundation work of improving the reconstruction efficiency. You see the reconstruction efficiency is 98%, extremely high, and is flat as a function of PT. And in particular, we have gained a lot in the low PT region, which is so crucial for the discovery of X24 lepton. So this foundation work was another key point for our discovery. So this is the present situation. Is the 4 lepton mass spectrum that we have in Atlas when you take the full data sample recorded so far. And you can see that the data points reproduce very well the expectation from the background from ZZ pair production coming from known standard model processes, which is shown here in red, except in this region here, where you have a huge excess. Forget about the blue stuff here, forget about it. You see there is a very big excess. In this region, we observe 32 events. The standard model background in red tell us that you should observe 11. And a Higgs signal give us another 16 events, and you can see clearly that the data are a much better agreement with the signal plus background hypothesis than just the background alone. And actually, if you look again at the probability that what you observe, this excess, comes from a fluctuation of this red thing here, you see the probability is 10 to the minus 11, very small. And also that the signal significance that you observe is 6.6 sigma. So again, also in X24 leptons, we are above the threshold for discovery. So the two channels are individually are above the threshold for discovery. Okay, we observe the signal also in X2W at the level of 4 sigma in agreement with the expectation. And now I go to the overall picture for the Higgs. When we put together all the channels together, we reach a significance of 10 sigma. So gamma gamma, 4 lepton, WW, tau tau, BB bar, we reach 10 sigma. 10 sigma means that the probability that what we observe comes from background fluctuation is 10 to the minus 24. Okay, so I think you are convinced that what you observe is a genuine signal. Okay, so we actually have moved already since a few months from the discovery phase, because now it's clear that the object is there, to the measurement phase. So we have started to measure this new particle. Did you get the joke? Okay, good. And I will show you a few examples. So we have measured the intensity, the strength of the Higgs signal in the various final states. This is shown here, normalized to the strength predicted by the standard model Higgs hypothesis, the so-called mu value. So mu equal 1 corresponds to a standard model Higgs, okay? And you can see here the various channels, BB bar, tau tau, WW, gamma gamma for leptons. So the combined value, mu, is 1.3 plus or minus 0.2. So you see that what we measure is at the level of 1.3 plus or minus 0.2 of the standard model Higgs boson expectation. So we are fully compatible with the standard model. The largest deviation from mu equal 1 comes from the gamma gamma channels. As already mentioned, we had a very strong signal in gamma gamma. We have also measured the mass of the Higgs combining the two most highest resolution channel, gamma gamma and 4 leptons, which give us the largest precision. And the mass is 125.5 GeV plus or minus about 600 MeV. So the precision is, does it work? Sorry, it's a bit difficult to, okay, okay, fine, better. No?
The position. Your position. Yeah.
Ah, I should be in the field, inside the field. Okay, good. So I should stay here. Okay, so good. So we measure the mass at, with 125.5 GeV plus or minus 600 MeV, 0.6 GeV. So already a few per mil precision. The mass is already measured with a few per mil precision. The measurement in the two individual channels, gamma gamma and 4 lepton, which used to be at 3 GeV, show a 3 GeV difference at the end of last year, is now down to 2.5 GeV. Due to most likely to statistical fluctuation in the 4 lepton channel. So this is a measurement of the mass. Then you can ask yourself, this plot shows the general agreement, the total cross-section of the Higgs signal compared to the standard model. We have seen that there is good agreement. However, as I showed you before, the Higgs is produced in several ways. Gluon-gluon fusion, vector boson fusion, association with W and Higgs. So it could well be that the overall signal agrees with the standard model expectation, but the individual production mode can show some tension between data and the standard model. So we have fit our data, separating the processes involving couplings to the top, like gluon-gluon fusion and TT bar Higgs associated TT bar Higgs, and processes involving couplings to W and Z, and this is shown here. So the standard model gives you 1 here, because it's always, what we measure is always normalized to the standard model expectation. And here you can see the measurement made in various channels, gamma gamma in red with their 1 sigma and 2 sigma ellipses, WW in green, ZZ in blue, and tau tau in yellow. And you can see that gamma gamma and WW, which have the largest statistics, have the smallest uncertainties at this level, and the other channels are less clean. But an important thing is that we have established non-vanishing vector boson fusion, this graph here, at the level of 3 sigma. We observe this individual channel at the level of 3 sigma, which is important because we start now to separate the various production modes. So it becomes more and more important. Now, another question that you can ask is the following, very important for new physics. Are there anomalous new physics contribution to processes proceeding through loops where you can have more particles? For instance, in the gluon-gluon fusion process, we have a top loop according to the standard model. Is there something else running in this loop that we don't know, new physics? Likewise, the Higgs decays to 2 photons through a W loop mainly, and also top loop. Are there new particles running in this loop? So we have fit our data, leaving as a free parameters a factor for this loop and for this loop. And we found that the standard model again is at 1, and this is what we measure. We measure 1 as a ratio to the standard model expectation with an uncertainty of plus or minus 20%. So again, we are, for the moment, within the present statistical power and experimental uncertainties, we are compatible with the standard model. But of course, we have to go deeper and deeper in our study and reach higher precision. So this is a summary of all the measurement of the couplings and production mode of the Higgs that we have done so far. I will not go through all of them, but just show, so they are all normalized. So these are experimental measurements, okay? Here the vertical black line with the 1 sigma in green and 2 sigma in yellow uncertainties, and 1 indicate the standard model prediction. So we have measured couplings to boson, to fermions, loops, various things, with various assumptions, various constraints, and you see that they are all aligned, almost in most cases, aligned around 1 with big error bars in some cases, but it's just the beginning, but we start to do serious Higgs spectroscopy and measurement. Okay, of course, with time, we would like to perfection these measurements, because by measuring the couplings of the Higgs with high precision, we can understand if this object is standard or a more exotic object belonging to a more general theory. And of course, we will be much happier if we find some deviations from the standard model expectation. However, exotic or standard, a feature of the Higgs boson is that it has to be a scalar. Actually, the first elementary scalar observed so far. If it is a scalar, I will try to convince you that within the present uncertainty, we think it's a scalar. So a particle with spin 0. And this is the first spin 0 particle discovered so far. It's a big revolution and has, of course, implication also in other fields like cosmology, inflation, all these things, of course. We have evidence. I think we can say that we have good evidence today that scalar fields, not only fermions and only boson gauge fields, exist. So this is very important. So to measure the spin of this particle and demonstrate that a spin 0, we have to look at the decay products, whose angular distribution keeps memory of the spin of the mother particle. So for instance, in gamma-gamma, we look at the polar angle of the 2 photons in the diphoton system, and we call it theta star, and we compare the theta star distribution in the region of the peak. You select the region where you have the spike, the peak, okay, the resonance, and you compare the angular distribution of the 2 photons to 2 hypotheses. Spin 0, which is expected to be flat in coseno theta star before cuts. So now, of course, we apply some PT cuts, experimental cuts, so it's not, this distribution is distorted. Whereas for spin 1 is excluded if the Higgs goes to 2 photons. And spin 2, when you compare so to the spin 2 hypothesis, like a graviton, graviton is a particle with spin 2, which the angular distribution should be picked in the forward region. So this is the cos theta star distribution in the data, the black points, compared to the expectation from the background. So in the gamma-gamma spectrum, the photons outside the mass peak, and in blue, the expectation for the signal. And you can already see by eye that the data indeed reproduce the angular distribution expected from the background plus a spin 0 object. But to be more precise, what we do, we fit the data with a likelihood function for the spin 0 and for the spin 2 hypothesis. We take their ratio and we compare what we observe in the data with the expectation from simulation for a spin 2 object here in red and the spin 0 object here in blue. And the black line shows the measurement in the data. So according to you, is it spin 2 or spin 0? So actually, you see that clearly the data favor the spin 0 hypothesis, and we are able to reject the spin 2 hypothesis at a 99.3% confidence level, which is extremely good. However, the rejection depends on the way you produce this graviton-like spin 2 particle. If it is pure gluon-gluon production, it's easier because the 2 distributions, spin 0 and spin 2, are more different. If it is QQ induced, it's more difficult, so there the exclusion is only at the level of 66%. We have done the same thing for X to 4 leptons, try to see if it is, if what we observe is spin 0, so really a scalar, or 0 plus, sorry, or 0 minus, so a pseudo-scalar. Again, the same game, we compare the data to the various hypotheses, and again, you see here the distribution for a 0 plus, a distribution for a 0 minus, and this is the measurement in the data. So again, the data favor the spin 0 hypothesis. Okay, so there are two additional questions that we would like to understand related to the Higgs sector. I'm close to my conclusion. Okay, just 2 slides and I've finished. Question number 1 is the following. Does this new particle fix the standard model problems at high energy? The Higgs boson, as of course the Higgs mechanism has been invented to give masses to the elementary particles, but also as a consequence of this, this process, WW scattering, in the standard model, violates unitarity at high mass. So if you take WW scattering at very high mass of the 2W system, TV or so, this process violates unitarity, means the cross-section diverges. So this process becomes unphysical. In the standard model, the divergence is fixed by the existence of a similar graphic diagram involving the exchange of the Higgs boson. So because there is Higgs boson, this graph does not, this process does not diverge. So we will need, but actually we would like to see if it's this cancellation, this fixing of the problem, works experimentally. So we would like to measure WW scattering at high mass and see if indeed the Higgs accomplished the task of fixing this problem, and if it accomplishes the task fully, or if there are some deviation from the standard model expectation, etc. This cannot be done now because it requires a lot of energy, so at least 14 TeV in 2015, and a lot of integrated luminosity, so it will be for the upgraded LHC phase. The other question is, why is the Higgs so light? The problem here is that in the standard model, radiative corrections to the Higgs mass involving top quarks diverge as lambda square, where lambda is the energy scale up to which the standard model is valid. So it's clear that if the standard model is valid all the way up to the Planck scale, granularification scale, this mass explodes. So what stabilize, is there a mechanism, a symmetry, which protects the Higgs mass from explosion, say from divergence? Is this mass stabilized by some new physics? And of course, we hope that there is something at the TV scale, like supersymmetry, in particular involving loops with a stop, which is the supersymmetric partner of the stop, which can stabilize this mass, because this graph, this correction, will have opposite sign to this correction, and so this will allow, will prevent the Higgs mass to become very large. We have been looking for stop quarks, so for supersymmetry at the LHC until now. We have found nothing, and in particular I would like to show you a very colorful graph showing our present limit on stop searches, to which, by the way, the SLAC group has contributed in a very important way. So this is a plan, stop mass versus plane, stop mass versus neutralino mass, and you see that we have excluded all this colored region here. In this region, stop going to top neutralino. In this region, stop going to bottom chargino. I don't want to become very technical, but you see that we have explored a large part of the parameter space, and we have found nothing. So of course I will be happy to answer more technical questions, but I don't want to annoy everyone with this with the details. So one word on the next step, and then a little movie, and then I'm done. So the next step, with the data that we have recorded until now in run 1, Atlas and CMS, each one about 25 inverse femtobar, we are going to continue to improve our analysis, to increase our sensitivity to the various Higgs final states and production modes, and in particular to measure the couplings and the spin with more precision. We think that by combining the Atlas and CMS data, we may reach you've seen Atlas alone has already 5 sigma, above 5 sigma in gamma-gamma for lepton alones. Combining with CMS, we should reach more than 5 sigma in WW, and hopefully also in tau-tau. BB bar is a bit more difficult. Combining Atlas and CMS, we should reach 4 sigma discrimination of spin 0 versus spin 2 and perhaps more, and we can of course measure the couplings with much more precision. Further ahead, so we have started now, just on the 14th of February, a 2-year-long shutdown. This 2-year-long shutdown was planned in order to be able to make a jump in energy, go to 14 TeV, because you remember in the accident on 19 September 2008 at 11:30 a.m., one of these superconducting, one interconnect between 2 superconducting magnets failed. So there are between 10,000 and 15,000 such connections in the 27-kilometer tunnel. So we have to open all of them, repair 15% of them, and consolidate all of them. This will take 2 years. So it will be a huge amount of work. And after that, we will be able to go to higher energy. So during this period, also the experiments are going to use this time to consolidate, do some repairs, improve their detectors. And I would like to show you a gorgeous picture, because for the first time since 3 years, we have opened the underground Atlas detector and cover and detector, and we have extracted a few days ago the forward muon, one of the wheels of the forward muon spectrometer. And you see in this gorgeous picture this wheel being raised up through the being brought up to the surface through the access shaft. So it's quite a spectacular operation. This object, of course, is quite a heavy object, so it's not so easy to do. So then we will resume in 2015 at close to 14 TeV, which is the design energy, yes, at higher luminosity. And we hope by the end of this decade to record 10 times more data that we have today. And then at the beginning of the next decade, we will have another long shutdown to bring the machine to be able to deliver more data and to upgrade the experiment. And by the end of the next decade, we hope to be able to record 100 times more luminosity than today. And with this, we will be able to observe some rare decay modes of the Higgs, like Higgs going to mu, which will give access to Higgs coupling to the second generation of fermions. Higgs going to gamma in association with TT bar, which will give us direct access to TT bar Higgs coupling, which is extremely important. We should be able to measure the couplings of the Higgs at the level of between 3 and 25%, depending on the final states, and also to measure the Higgs coupling to itself, which is a fundamental piece of the standard model Lagrangian, and is very important to understand how the Higgs potential works. Okay, before ending, a little cartoon. Well, it's not a cartoon, it's reality, it's not a simulation, this is data, showing how the signal was born and how it evolved with time. So we'll start with X2 gamma, and I will show you. You have to be very, sorry, what's going on there? Something, oh no, it doesn't work. Okay, this one works. So this is X to 4 leptons. So you see, as a function of time, this is the time going up, the luminosity, what we have been observed. Each histogram is refreshed every run, so every typically 12 hours, something like that. So you see the data points which reproduce very well in red the standard model background, and you see here the signal goes up here. And then we compare this with the Higgs expectation in blue. This is the Higgs expectation. And this is Higgs to WW, 2 leptons, 2 neutrinos. So again, the data point in black. In blue, the background coming from other processes than the Higgs, dominated by WW pair production. You see that the data are above the background, and the significance increases with time. And then at some point, at the end, we will add in red the prediction for the Higgs boson signal. This is the Higgs prediction, and you see that it's quite impressive. I don't know why the X2 gamma does not work. Why it doesn't work? Okay, sorry, it doesn't work for some reason. So conclusions. The first LHC proton-proton run just ended. It was gorgeous. It was an extraordinary achievement. The experiment, well, I'm talking about Atlas, but this is also true for CMS. We have recorded something like close to 30 inverse femtobarn. The experiments have been operating extremely in a very effective manner, very smoothly in all their components, from the detector to the trigger, software computing to the release of the physics results. These 3 years have been extremely demanding, extremely challenging. The machine, the experiment, the computing has been stressed beyond design performance, and also people. I can tell you that we had to perform beyond design. It's true. So Atlas has already a very huge physics output, which is summarized in 240 papers on collision data and 470 preliminary results presented at conferences. They cover measurement of standard model at 7 ATV, with increasing emphasis on detailed, exclusive, and complex final states, searches for new physics in a huge number of topologies and testing many scenarios. And now moving to higher energy is very important to make a quantitative leap. And the fantastic discovery of a very special particle, which indeed looks like a scalar. And so this is really revolutionary. It's the first elementary scalar that we have found, and we have demonstrated that a scalar field exists. I think also, it's very important that to stress that the era of precise measurement of the new boson has started, and in parallel the quest for new physics at the TEF scale continues, and of course the LHC in the next step of the LHC, higher energy and then upgrade, will have a lot to say. So we hope that this discovery is not the only one. These accomplishments are, of course, the results of more than 20 years of very hard work and ingenuity and extreme dedication of those involved in the LHC project. But I think that more in general, they are the results of the vision, ingenuity, and painstaking work of the full high-energy physics community involving accelerator people, instrumentation people, computing, experimental physicists, and theory. Thank you. Well, so the splices, we call them splices, these interconnects. Well, we are confident in the sense that we are not only going to repair those that we think. So we have developed, the accelerator people have developed a certain number of tools to measure the resistance of these interconnects. They've done over the last year a lot of measurement, both for the superconducting interconnects and also for the classical copper interconnects. And so they have detected those that need to be repaired, and they will act on them, but also they're going to consolidate all of them. So it's a preventive measurement to, even those that are healthy are going to be fixed in order to be completely solid. So I think that there will be no problem with that to go to higher energy. The question of the training of the magnets, we think that with a reasonable number of quenches, so few per magnet, we can go to 6.5 TeV per beam, so 13 TeV in the center of mass. Going beyond that, it seems that beyond 13 TeV, then you really start to need several dozens of quench per magnet, and this becomes impossible because, of course, you have 1,200 magnets, 27 kilometers of machine, and then it becomes impossible. You take an enormous amount of time, and also you also risk to damage the magnet itself. So we will most likely prudently run at 13 TeV in 2015, and then later on perhaps go to 14 TeV after some operation and some machine commissioning and stressing the machine at 13 TeV. We will go higher. No, I think there is no problem from the point we are. I think confident that it will work because really the plan consolidation and repair works is extremely conservative and extremely redundant. So I don't think there will be any problem.
I didn't get a sense from the presentation of fluid examples, this increasing pileup at higher luminosity starts to limit the analysis. Are you seeing that in some of these rare channels from Higgs that pileup is starting to introduce enough uncertainty?
So, yes and no, in the sense that until now we have been able to, by developing quite cunning, quite clever algorithms, and with a lot of ingenuity work and preparation work, we have been able to run with efficiency and performance for the main physics object, electrons, photons, B jets and jets, etc., missing energy, where essentially the pileup has very little impact, both in terms of efficiency, reconstruction efficiency, and resolution and performance. One thing that I would like to mention is that it's extremely important to have a constant efficiency in terms of reconstruction and identification for electrons and photons as a function of pileup. Why constant? Because during the duration of a field, which is typically 8 hours, when you inject the beam at the beginning, you have 40 events of pileup. At the end, you have 7, 10. So if your reconstruction efficiency varies as a function of the number of events per crossing as a function of pileup, then corrections become a nightmare. You have to correct the efficiency as a function of time inside the field. The systematics become a nightmare. So the effort that is being made is to make the identification efficiency very robust by using variables to identify electrons and photons, which are very little sensitive to pileup. So up to this level of 20, we are okay. We are now preparing for the next phase to be able to swallow up to something like 80 events per crossing by the end of this decade. It will affect the performance, but to some extent, of course, but we are also becoming more clever with time. And so we think that we know now that the object is there, so we are not looking for it. So we will refine also our analysis to try to be able to compensate for that. I think we have to be able to swallow up to 80 events per crossing or something like that by the end of the decade. Then, of course, in next phase, in the next decade, we will replace the tracker, so we will have more granular tracker, so we will be able to face. Of course, for the calorimeter, the situation will not change. We are not going to replace the calorimeter, so we will have to swallow it. But we are confident that we have seen how well the experiment, not only Atlas, also CMS, we were not expecting such a pileup now. Atlas and CMS have been designed for 20-23 interaction per crossing at the highest possible luminosity. And we reach up to 40 now in this pre-lumin. So demonstrated when you have data, of course, you can do much better than the most optimistic expectation based on simulations.
Oh, go ahead, yes.
Are neutral particles like K longs that you cannot easily associate it with a vertex? Is that a significant problem, for example, trying to measure missing energy, transverse energy?
Well, transverse energy is mainly measured by looking at the energy in the calorimeters. And K-long, this particle usually is quite soft. They're not particles which give you a huge amount of energy. You are dominated by the component coming from jet fragmentation. No, we're not particularly limited by that. Of course, we use mainly calorimeter. We also use the tracker. So some of the particles that are not measured by the calorimeter. Okay, so neutral particles like neutrons, for instance, are measured in the calorimeter. So there is no
no
problem.
Can you associate them with a vertex, since you have 20 or 40 or 50 interactions?
Very good question. So we have developed techniques to associate the soft components. So when you measure the missing energy, okay, when you using your detector, there are various components contributing to the missing energy. In your event, you can identify already if you have jets, electrons, and photons. These events are can be easily associated to the vertex because they are high PT objects. The electron, and photon, and the jet can be easily associated to the vertex. There is also a soft component of the missing energy coming from soft stuff that is not easy to associate to the vertex. So we have developed a technique by which we associate to the measurement of the missing energy only a fraction of the soft component which has tracks associated with the main vertex. So there's been a lot of work to try to improve the resolution. And actually what we observe is that if you don't do anything, so if you just, how to say, look at the full energy in the calorimeter and you calculate the missing energy as a function of the pileup, the missing energy, even for events which have no genuine missing energy, like z to mu mu, it explodes. But then when you apply constraints coming from tracks, from verticing, then you are able to keep it, keep the missing energy resolution at the affordable level. So, but there's been a lot of work on that as well.
Do you have a plot which can give us an idea of LHC 13 reach for supersymmetric particles?
I have a plot, but I'm not sure I have it here. I have it, but not in this presentation. So I can show it afterwards privately. You know, we have a nice plot showing the reach for stop, etc., which goes well, which extend well beyond the TV region. So at least not, of course, for all configuration, not for all mass difference between the stop and the neutralinos, but I will show you afterwards.
The other question is, I hear that CERN is already thinking ahead for a 33 TeV upgrade.
So actually, the maximum energy that you can achieve using the present tunnel, which is, as you know, limited by the magnetic field of the bending magnets, the maximum that you can achieve is 33 TeV, because if you think in a time scale of 10, 15 years, 20 years, what is the maximum magnetic field that dipole can reach today is 8.3 Tesla. We think that we can reach 14, 15 Tesla, something like that. Okay, this is the maximum achievable, so this will give you roughly 33 TeV. So we are really clearly limited by the bending power, the technology for superconducting magnets, which gives you the bending power, which can keep high energy proton beams inside the 27-kilometer ring. If you want to go to higher energy, you need a larger ring.
Okay, any other questions?
After observing all this data for such a long time, is there anything that strikes you as something reliably anomalous, and especially reliable at all, like this H to gamma too large, or these two masses instead of one, whatever? Something which requires going beyond standard model, some hints that you know that it is going in the direction of finding something reliably anomalous.
Beyond what I've shown, or what I've shown?
Already, among what you have shown, is there some single thing which grows into the direction of, oh, this is something which...
Okay, so first of all, when you say the two masses, I will say no, and I tell you why. Because, so what you're alluding, Andrea, I guess, is the fact that we measure the mass of the Higgs boson, okay? So when we fit our data by using both channels, gamma gamma and X24 lepton, we measure this mass. But if you look at the individual mass obtained in the 4 lepton channel, so we fit the 4 lepton peak, then we fit the gamma gamma peak, then we find masses which differ by 2.5 GeV. This difference used to be larger with the previous amount of data until, say, end of the data recorded until September, 3 GeV. Now it has gone down by half a GeV. Why? Because the 4 lepton channel has just a few candidates. So it's 2 or 3 candidates going on the high side make a difference. Actually, we got a few more candidates which pushed this mass up. It used to be 123.5, and now it's 124.3. Okay? Now, these are not 2 particles. This is just 1 particle, and demonstration is this plot here. You fit your data, you get 1 peak. Okay? You don't get 2 peaks. The p-value gives you, when you fit your data, you just find 1 peak, even if you remove the systematic uncertainty. H to gamma gamma, yeah, X to gamma gamma is higher than the expectation. The mu value is 1.6 plus or minus 0.6 or 0.7, something like that. No, listen at 0.4, something like that. It's a 2.4 sigma from the standard model. 2.4 sigma. We have to combine with the other experiment. And the other experiment, unfortunately, you have to rely on Atlas for physics beyond the standard model because the other experiment.
So you saved something most important to the last phrase.
No, so we are at the level of 1.6 plus or minus 0.4, so we have 2.4 sigma from the 2.3, 2.4 sigma from the standard model, which would you claim a discovery with 2.54 sigma? No. So we have to see and how if the error shrinks and the excess remains, of course, can be something, but then we'll have to combine with the other experiments ultimately. And